So hello everyone. I'm Zeyuan from IHF Beijing. So I will present the latest results from the Daya Bay experiment. So I believe you should have seen my screen. Let me use the full screen. Yeah. Okay. The Daya Bay experiment detected the reactor antineutrinos for the Zeyuan measurement as well as the study of reactor antineutrinos. For the reactor antineutrinos, they are electron antineutrinos produced in the nuclear reactor core. They primarily from the beta decay of the fission fragments of the four major isotopes, 2 urium and 2 plutonium. We detect the antineutrinos using the inverse beta decay. The antineutrino reacts with a proton, releasing a neutron and a positron. The positron will form the prompt signal, and it carries most of the neutrino energy, while the neutron will be eventually captured either by the hydrogen or by the gadolinium, releasing the delayed gamma rays. The Daya Bay have 3 experiment halls to do the near and far relativity measurement and to compare the neutrino flux and the spectra to determine the neutrino oscillation parameter. And we have 8 detectors and 6 reactor halls, and I will not read the details. And the Daya Bay experiment started the taking from the 2011, the end of 2011. Now the taking has been officially stopped at the end of 2020, and we have 9 years taking. And this photo shows the decommissioning ceremony, and after the ceremony, the decommissioning, including the detector removal and some other stuff, started. Now all the decommissioning has been finished. So for the data set, we have our data set lasts for 9 years, the 3 experiment halls. Now we are analyzing the data after the September of 2017, and we expect our final result in the next year or slightly later. So the data used in this talk only covers from the start of the data taking to the September of the 2017. So I will go through the physics results using the data set. And in the data set, it's about 2,000 calendar days, and we have more than 1 million and 50,000 and 1.5 million IBD events in the 2-year halls, and about 0.5 million at the far hall. And this plot shows you the comparison of the predicted neutrino rate and the measured one. Yeah. Using the dataset, we published our oscillation results 3 years ago, and the Z13 value is the most precise one to date. And after that, we did some sterile neutrino searches. And in particular, the combination between Daya Bay and MINOS and can include the LSND and the mini-Boeing signal region at 90% confidence level for the delta M squared for 1 less than 5 EV squared. Yeah. And as a well-functional detector, we performed the measurement of the neutrino flux and the spectrum, and they're published in the PID for the flux and for the spectrum, the total spectrum, it is published 2 years ago in the PRL. And we can find an observed flux deficit using when comparing our data to the model, the so-called Huber and Mueller prediction model. Yeah, and also you can find the Daya Bay results is consistent with the previous experiment at the flux. And for the spectrum, you can see the data and prediction shows an overall 5 sigma deviation. And at about 5 MeV, the local deviation is larger than 6 sigma. Yeah. And we also studied the neutrino flux and spectrum evolution versus the field evolution. As we mentioned before, the antineutrinos come primarily from the Urium-235 and Plutonium-239, and the neutrino yield and spectrum are different for the 2 isotopes. So when we fit the neutrino flux evolution with the plutonium fission fraction, we can obtain the antineutrino yield of the Urium and the Plutonium, as shown in the left figure. You may find the Urium is very responsible for the neutrino flux deficit, and for the Plutonium, the prediction, Huber-Mueller prediction, and the data agrees well. Later, we studied the spectrum evolution. We extract the spectrum of the 2 isotopes, the neutrino spectrum of the 2 isotopes from our data. Yeah, we can find a similar bond for the 2 isotopes in the 4 to 6 MeV region, and the deviation, the local deviation for Urium is up to 4 sigma. And for plutonium, due to the larger uncertainty, it's only 1.2 sigma. Yes. Based on this, we have built a database prediction for the other experiments. We convert our neutrino spectrum to our prompt energy to the neutrino energy, and with known reactor phase interaction for example, the other reactors, the technique can predict the energy spectrum to a 2% precision. The paper has been online in this year in the supplemental material, and you may find the data, the tabulated data and the examples. A final update about the neutrino spectrum is a joint analysis between Daya Bay and the Prospect. The Daya Bay running at a commercial nuclear reactor power, and Prospect is running close to a research reactor power, and it is a high Urium concentration, while Daya Bay is low. So the comparison shows the consistent results between the Daya Bay and the Prospect. The measured Urium-235 spectrum is consistent to each other, and also with the constraints from the Prospect, Daya Bay also increased the precision of the measurement. In particular, we reduce the correlation between the Urium and plutonium by 20%. And the paper is also online now. So the quick summary, we are analyzing our final data set. We expect a final precision of sin squared 2013 of 2.7% is likely to be the standard for the decades to come. And we have performed many studies on the neutrino, flux, and the spectrum. And our final results are coming in next year. Stay tuned. Yeah, thank you.